Okay, so let's get started again. Today we're going to talk about the first unit in the Bjc Curriculum, Beauty and Joy of Computing. So here's how you get to the curriculum, okay? We have the URL, which is bjcedc.org, okay? That's where you go to get started. When you go there, what you'll find is this page that kind of shows you a whole bunch of things. But if you look here at the bottom, and I kind of enlarged it here. If you look at the bottom, there's a button that takes you to the curriculum, and that is right over here, right? This is the curriculum page, okay? So that's what you want to be able to get to. And I won't walk you this way again, right, for the rest of the time, but this is how you get to the Bjc Curriculum. And by the way, if you simply Google Bjc Curriculum, this is one of the first pages that gets offered. This is actually a partnership between the folks who built the curriculum in the first place that come out of UC Berkeley and the state of New York that kind of sponsored this curriculum throughout their state. So this is actually well, it's food by the state of New York is being practiced all the time, and it's become the default curriculum. So it's not even on the Berkeley side anymore. They just reroute you to this place. So let's see what we have. Unit 1 is an introduction to programming. It's very, very gentle introduction, which is exactly what we want for the students. And the very first lab, and I should say that the units are always broken down into perhaps 5 labs each, maybe sometimes 6. But basically, this first lab is just simply to get the students used to working with programming, okay, and getting them started. So the first thing that he'll ask you is the quote, click Alonso game. Alonso is that fish-looking thing over there, and that's the mascot for Snap, okay? So what we're gonna do is just build a game. The object of the game is simply to click on Alonso, okay? Now, what I'm showing you here is pretty typical of what you'll see in all of these units, okay? So notice that this is actually a video, okay? So you'll go to this web page and you'll find lab 1, lab 2, lab 3, and inside each one of those there'll be some text to guide you as to what you're supposed to do, right? And there will also be some videos to kind of help you learn how to do it. So like this particular video that I just dragged the screenshot from, this particular video will actually walk you through how to complete this lab, okay? So they're very, very useful. Something else that you'll see a lot in the videos is like this. This is actually a snippet of code, okay? So you take that snippet and they might give you a challenge like, oh, modify it so it does the following, okay? That's what the students are going to do. That's what you're going to do in this professional development. So it's kind of nice that they actually walk you through how to do things. It's not a tutorial in the sense of do step 1, do step 2, do step 3 that you can get through without thinking, just kind of copying what they said in the tutorial. You won't be able to get through without thinking, but you wouldn't want to, right? You wouldn't want your students to do that either. What you want them is to learn something along the way. And this really is more of a guided walkthrough, kind of like going through a nature preserve or something that you can have a guide or some kind of write-up that tells you, okay, so I should be looking at this right now and this is what this means. That's what you have, okay? So we'll see those, right? Now, what exactly happens in the Alonso game? The very first thing that you do is just like the hour of code. Beauty and Joy of Computing actually has an hour of code that you could run with like elementary school kids or somebody who hasn't seen any computer at all. And the first part of that is actually pretty much the same thing as what's happening in this particular lab in this unit, okay? So yeah, you just start out with that. Very, very simple stuff. Now, something else they introduced early on is the idea of pair programming. Now, pair programming is actually an industry practice, but in the classroom, the way it looks is like this. You have John and you have Sally, okay? And they're both working on the same computer. At any given time, either John or Sally is typing, and the other one is providing helpful advice, right? Now, generally what helpful advice means is skeptical advice, okay? Meaning, I don't think what you're doing is right, okay? And the reason you need that is because when you're programming or you're doing something creative, it's easy to get lost in the flow and kind of put a bunch of stuff together without thinking critically about it, right? So that critical perspective is what the other person brings. Now, the other thing that happens is John is typing along and it's like, I'm stuck. I don't know what to do. This is too hard. Sally steps in and says, okay, give me the wheel. And she starts thinking through it. She makes more progress. This is great, okay? So that's kind of the good stuff about pair programming. You may be thinking to yourself, what is to keep Sally from hogging the monitor and John never actually gets the program, okay? That could happen, but inside the unit, they actually have signposts where they say, okay, now swap, okay? And so whoever is using the computer steps out of the way and lets the other person in. That's really built into their labs, okay? And in general, I kind of take it as our responsibility to make sure that doesn't happen, okay? Hopefully we don't have so many students in the class that we can't actually monitor and see, hey, wait a minute. I'm always seeing this person on the computer. Go in there and tell them, hey, it's time to do a swap, okay? So is it a good idea or a bad idea? Personally, I'm torn. I think if the students are left to themselves so that there's just one per computer, what ends up happening is that when they do get that moment of panic, that moment where they go, I don't know what to do, we tend to lose them, right? Because they panic. I have actually been in classrooms where the next reaction is to say, this is so hard. Oh, look, there's a game going on in this web page. And they go off and they start playing games. And it's like, no, that's not how you deal with hardship, right? But again, that's part of what we're trying to teach them. Even the math practices say, we got to help our students learn resilience. So that's one of the things that we wanted to get out of this class. Again, that's what we're doing. So I kind of like pair programming because it prevents that. I kind of worry about it because it can lead to, oh, good, I don't have to think because my partner is doing the thinking, right? We don't want that. So you just have to be aware of what's going on. Now, some other things you learn in this lab are things like how to do random movement. This is important for games, right? You want a spaceship or whatever to be able to move apparently randomly. In here, Alonso is not going to just sit there and let you click on him. It's going to move around so that the game is a little more challenging. We'll also see forever loops. Do the following thing forever. Just keep repeating it, okay? That's a great computer science concept. Kind of a specific snap concept is costumes, meaning that you see the fish, that's Alonso. It doesn't have to be a fish. So for example, in one of my little programs, I actually have Doctor Who shows up instead of a fish or instead of a turtle or instead of whatever. We can just change whatever that sprite, that's the technical term, whatever that sprite looks like, okay? We can make it be anything we want. Part of the game is when you click on Alonso, it gets a little bit dimmer, eventually it disappears. You can't see him anymore. That means we're adjusting the brightness of Alonso, something else that happens in this game. The smallest thing that happens is probably the most important for the rest of the course. That is how to save a program, okay? We can't just start from scratch each time. We need to be able to save what we have. And that's something that this teaches you how to do. When you save the program, it's important to share it so that other people can look at it. I find that with my students, I simply ask them to save the program shared and then send me the URL to the shared program. That's how I can grade it. You may or may not like that. The downside of doing that is that when it's shared with everybody. So everybody can see it if they know the URL. You may not want that, right? So there are other alternatives. You can actually save it locally and then they can send you a file that you can see. But still, you have to work through that process, how you want to run your classroom. And if you want to simply use the sharing mechanism to be able to look at stuff, that's what they introduced in this particular lab. If you want to do something else, just have them learn how to export, and then you can do that, okay? All right, now let's look at the second lab in this unit. The second lab is called Gossip and Greet. And it does have really a lot of interesting things. So the first thing it does is it starts out, just first activity, it says, hey, we wrote a bunch of blocks for you, right? These are new blocks. These are not kind of the blocks that you started with. These are custom blocks for this lab. Go see how we built them, right? So they teach you how to edit a block so you can look at the definition. You can kind of peer inside of it. That's amazing. Well, what's that doing is it's helping you understand how new blocks can be made so that you can make your own new blocks. Boom. That's the very next activity, okay? So these are very well thought out. That's part of what I want to show you, okay? So what else do we learn in this lab? We'll learn about lists, okay? We'll learn about manipulating words. Hey, let me tell you, this is huge. Because when you're talking about computing, even the words computing, okay, we're thinking numbers, right? And a lot of people think that computing is all about numbers. And actually, computers can deal with words just as effectively as they do with numbers. That's something that perhaps gets lost in a lot of introductory courses. So no, here we are, Unit 1, Lab 2, and we are immediately working with words instead of with numbers. I think that's pretty cool. Some other stuff that you'll see, how do I change my sprite so that it looks like something that I developed, okay? This is a fun little mini activity that your students can do, is just go off and build their own sprites, use a little paint program and actually do something really neat. What backgrounds do I have? And you might be surprised at how creative the students can be at building these backgrounds. They can be space themed, they can be mountain themed, etc. Some of us actually believe it's a great place for the students to kind of express their own cultures, their own backgrounds. Okay, so let them run free and do whatever they want there. We're already showing them how they can change the background in their system. In this lab also, we want to talk to the user. That's kind of the idea. This is not as fancy as a chatbot, but it's as close as we can get in Unit 1, Lab 2. And so we want to ask the user for their name. Who are you, right? What's your name? And the user types in, hi, I'm Sally. Okay, well, actually, don't do that. Type Sally, otherwise you'll confuse the program, okay? But then we can come back and say, oh, hi, Sally, nice to meet you, right? So that's the kind of thing that we want to give in this interaction. Except, of course, if Sally plays the game 5 times, the 5th time she types Sally and the computer comes back with, oh, hi, Sally, nice to meet you. She's going to be suspicious that the computer doesn't actually know her at all, right? So we can actually write the code so that it says instead, I've already talked to Sally. So maybe I should respond with, hey, Sally, nice to see you again, right? How do I know if I've already seen Sally or not? I'm going to remember all the names that I've been told in a list. What's a list? Just a collection of, in this case, names. The first one, the second one, the third name, right? And so we can check to see, is the name that I've been giving in that list or not? If it is, I've already seen you, okay? If it isn't, right, then I'll add you to that list and say, nice to meet you, right? So those are actually pretty advanced computer science concepts. I mean, when you're teaching an introductory computer science course, say, Java 101, even at the college level, this may not be what you lead with, okay? One of the beauties of Snap is that it actually makes these kind of things easier, so we can introduce advanced computer science concepts early on. So concepts that are flying around here, if statements, conditionals, like is this name in this list, and then being able to change what we say based on that. All of that is happening here. Is very, very nice. Okay, so let's move on to the third lab in this unit, and that is exploring motion. And this is a favorite lab. Okay, a lot of people really, really get excited here. And it has a direct kind of tie to something called turtle graphics. Some of you may remember a programming language called Logo, okay, that introduced the concept of turtle graphics. And then you have a little turtle in the screen that can move by so many steps, that can turn by so many degrees, and it has a pen that it drags around. So when it moves, you can actually see its trail. So it was a favorite of kind of introductory computing. I actually used it to teach 4th graders. Gosh, I mean, it's starting in the 80s, but I used it when I came to Wyoming in 2000s, early 2000s. So it's a great first programming language, and it is fully incorporated into Snap. Okay, so one of his sections is, in fact, pretty much might as well call it turtle graphics. They call it motion and pen. Okay, well, whatever. But that's something that we'll introduce in this particular lab. The other thing that we'll introduce is kind of a tie-in to paint programs. And the one that I always think of is Microsoft Paint, that lets you put geometric shapes, circles, triangles, squares, rectangles, and color them, right? So that you can have a blue rectangle next to a red triangle and so on. We can do all those things, right, with the stuff we're doing in this lab. And finally, we connect it to modern art. Okay, that's a little ambitious, right? I mean, it's not clear that we're really achieving, quote, art here. But if you look at this slide here, these are actually pieces of art that you can find hanging in museums, right? And this is the kind of thing that we can do with the graphics system. Hey, you know what? It kind of belongs there in a certain sense, okay? So maybe it's not that much of a stretch. Like I said, I found students that just really, really love this section. So let's talk a little bit about how we might do this. This is something they give you. This is a little program they give you. It says repeat 4 times, move 100 steps from here to here, okay? And then wait a couple of seconds. Okay, now we're gonna turn 90 degrees and just keep repeating that. So now we'll move that way, turn, move, We're back where we started, okay? What just happened? Hey, I walked in a square. I know it's a square because each time I moved by the same amount, and each time I turned by 90 degrees, I did that 4 times. I built a square, right? So they actually give you this challenge. Here's this bit of code. What does it do? Spoilers, it's a square, okay? Now, here's the next step. This is the most important step. You now can fiddle with this, okay? What do I mean by that? You can play with this. You can hack with this, right? That's what computer scientists call it. By the way, hackers, not necessarily a bad name, just people who play with computers, okay? You can have fun. That's really what we're talking about. So what kind of fun can we have? Change the degrees. Not 90 degrees, let's do 40 degrees. Let's see what happens, okay? By the way, if you do that, it's not gonna come back to where you started with, right? Well, maybe you need to change the 4 and repeat 4. Okay, that might work. So if I go by 40 degrees, what do I need? I don't know. Bunch of times to be able to get to the beginning, about 9 maybe. I don't know, you try it, see what happens, okay? You might want to change the pen properties, the size. I want thick lines, I want thin lines. The color, red, blue, whatever you want, okay? Maybe every different line is a different color. Have a blast, right? Whatever you want to do is perfectly fine, okay? I will warn you this. Maybe it's not so much of a warning, but I have come to this place when I'm working with students, especially elementary school students, also high school students, play, and they go off and they do just what I said. And the entire day is lost, okay? Because they have so much fun playing, and I gotta warn you, one tiny little mistake in here, quote mistake, can lead to absolutely beautiful art. So like we say, repeat 4. What happens if you say repeat 400? You still have a square, right? Okay, I went through it 100 times, but we still just build a square. Okay, instead of 90 degrees, what if we do 89 degrees, but repeat 400? All of a sudden, it never quite lines up, so it's a little bit off, and you start building these beautiful geometric shapes. Some of you may have grown up in the ages of kaleidoscopes as kind of presents, spirographs, right, that you give children. Okay, yeah, that's what we're building, right? So it can be really cool. Sometimes it can be hard to bring them back on task. It's like, hey guys, we're going to build polygons. Polygons? Anybody interested in polygons? So it gets a little rough there. In the grand scheme of things, it's just a blast. Let them have fun, right? I mean, that's part of what we're trying to do, is get people interested in computing. Okay, so we did squares. Now, instead, let's try something new. Let's say that we go forward 100 steps, and then we come backward 100 steps. So we drew a line, right? But we came back to where we started. Then we turn 100 steps back, turn 100 steps back. So what we're building is no longer a polygon. What we're building is an asterisk, okay? So there you see a couple of different asterisks. One of them has 5 little steps. The other one has 3, right? So how can we actually do that? Well, you can experiment with the repeat how many times, right? And with the turn, how many degrees. Here's a spoiler. If the number of degrees is 360 divided by the number of times you repeat, then it's going to be evenly spread, right? So you can do that, right? So in this case, for example, this code, it repeats twice and it turns 180 degrees. That's actually going to build something that looks like this, right? So it's a straight line without any obvious beauty that in fact has been drawn by going up, down, down, up, for example, okay? It just looks like a straight line. 3, repeat 3 times, and 360 divided by 3 is 120, so that's what you would turn, and so on, okay? So that's how you build these. And again, I'm trying to, or I should say the Bjc curriculum is trying to get the students to explore, okay, to play, and let me tell you, to not be intimidated by the computer, right? Let's see what happens. Oh my God, I made a mistake. Look, it still looks pretty. It wasn't that bad, right? Now let's try to work towards the ideal shape that somebody has shown me, okay? All right, let's make it even more interesting. Instead of starting, going 100 steps and coming back 100 steps, what if we only come back part of the way and then turn, okay? It's actually hard to visualize, okay? Maybe some of you will find it easier than I do, but what you end up building are these kind of pinwheel looking things, okay? So in the inside of it, it looks kind of like a polygon, but it kind of overshoots at each step, okay? So it's quite pretty. These are actually quite pretty. And here, the Bjc curriculum takes a really big step, and it says, it is time for you to write your own block. Because, we've been playing around with the idea of how many steps do we take, how many times do we repeat, how many degrees do we turn. Let's just codify that into some block of code. So right here we had repeat. This does 21 times. I wouldn't want to do that in my head because 360 divided by 21 does not sound fun. But that's the kind of thing that computers are actually pretty good at, right? Computation. So it says if you tell me the number of branches you want, that's actually what you go on the repeat, right? It should be repeat however many branches I want. And then what I want to turn is exactly 360 divided by the number of branches I want. So you see that I can now build a program that is more general than just build a 5-sided pinwheel, build a 3-sided pinwheel. It can build any sided pinwheel. You just have to pass in those values. Okay. So this is a huge step for the students' development because now they're writing their own blocks, right? I mean, we've been leading them up to this. This is pretty cool. All right, you know what? That wasn't enough. Let's generalize some more. Okay. We talked about earlier how this kind of same idea builds you these pinwheels. If you don't come back at all, right? If you simply go and then keep going, then you build a polygon. Okay. If you come back all the way, then you build an asterisk. The pinwheels are kind of in between asterisks and polygons. So what we can do now is actually build another block called polygon that simply calls pinwheel with the right set of parameters to make it build a polygon, right? We can build an asterisk block, right, that calls the pinwheel block with the right set of parameters so that it builds a pinwheel. You know, again, spoilers, to build a polygon, it should never go back at all. To build an asterisk, it should go back all the way to the beginning. So that's how we can actually use that same block that we already wrote to do two different kinds of behavior or seemingly different kinds of behavior. We're really kind of layering it thick, but we're driving the point about abstraction, right? And abstraction is something that happens when you can perhaps use another resource in a way that's more general than what it was originally intended. That's not a good definition. I'll give you a better one when we actually talk about the next unit. But you see, we're preparing students to see that, and so this is a great moment in this whole thing. Okay, this is actually what I talked about, which is the abstraction part. So I'm just going to skip this. And instead, I'm going to kind of come here to the end. We've been building polygons, right? We've been building all these sort of shapes. Let's just keep doing it. And now we're going to introduce a new type of loop. Before we talked about the repeat loops. Repeat 7 times. OK, those are nice. Those are easy. You know exactly how many times it's going to go through. Now we're going to do a more general kind of loop. And it's called a for loop. And it actually also loops a fixed number of times, like say 10 times. The difference is that you know whether this is the first time you're going through the loop, or the second time, or the third time, or the 5th time, right? Whereas in a repeat loop, you don't really know which time it is, right? So that's the difference between for loops and repeat loops. Boom, we introduce them right now. Repeat loops are not very common in other programming languages. For loops are very common. They're in every single programming language. So this is actually a good time to introduce them. Okay. So here are some of the projects that the students can build. You can see there are a whole sequence of squares that get a little bit bigger. You can see they're a spiral, right? And what's changing is that we're not quite turning enough to make it into a circle. We're turning a little bit less than necessary. So that kind of expands into a bigger circle, kind of a little bit at a time. This next one is one of my favorites because you build a triangle, and then over the same baseline you build a square, and over the same baseline you build a pentagon and a hexagon and so on. So you can have this kind of beautiful effect that's shown here. These are all sort of beautiful. They're creative. They're little bits of art that the students actually have enough code to be able to generate easily. So it's super cool, right? And just end with emphasizing art, right? Again, what I really want to emphasize is not so much quote art, okay? It is fun, right? I mean, this should be just the students should have a blast exploring these things. So in the final kind of activity in this lab, they're encouraged to build just little pieces of art. Some of these are built by writing a program, like the one in the middle is actually done using the pinwheel and then moving it around and doing some more pinwheel. The one at the top, okay, that's actually just geometric shapes, so it's polygons. But the way that they've kind of assigned that activity is that you place the polygons where you want, okay? So it's not so much, there's a program that builds that at all. there's a program that builds each one of the individual elements, a square, a circle, a triangle, and then the students kind of drag things around and then say, oh, stamp a triangle here, boom, right? Stamp a square there, boom. And so they're actually using the computer kind of as a paintbrush and a canvas. So, they can go here and draw something there, draw something there. This is the Microsoft Paint way of building art, okay? So it's creative, it's fun, it's interactive. I think of it as a reward, okay? We've been teaching you how to program. You've actually starting to get good at it. Now go ahead and have some fun, okay? So at least spend a day just having fun. This one is a trick. This one right here, that's actually not drawn as a computer. That's a real piece of art that's hanging in a museum someplace. So you can see that we're not far off. Okay, you have to be creative, right? That's why they're artists. But our kids could actually build something that's fairly similar to that. And I think that's extremely empowering. So yes, let them run through. Okay, the last programming lab in this section is lab 5, and it's called Follow the Leader, okay? So now that we've done a lot of art, we're gonna kind of push through on the idea of movement by giving a sprite a target to move towards, okay? Now what is this target? It's actually a different sprite. And the different sprite you can move around simply by clicking on it and dragging it, okay? So it's here, I've dragged it as here, I've dragged it as there. The other sprite has got the job is to go, ooh, there's the one I'm trying to follow, let me get closer to it. It moved, okay, let me follow it. And honestly, it's you can write this code so that the sprite has no chance of getting to its intended target because it moves so slowly. You can always just get out of its way. Or you can write it so that it gives you no chance to move out of the way because it says, oh, there it is, zoom, right? It's like, got me, right? But that's the game they're writing, okay? So notice that we're actually writing pieces of code that could later become a real programming challenge, like an actual game that's developed. Think of Pac-Man and Pac-Man being chased by the ghost, okay? That's kind of what we're building here. Why is that important? The students are going to build a program to show off to the College Board in what's called a create task. Here they have good prime starting place for that, okay? One thing else that's done in this program is there's a place where you kind of check, oh, did I find the other sprite, right? Did I get there? In game programming, that's called collision detection, right? And it's very important. So for example, you can see when a missile hits a target, that's a collision that's detected. Or when your car hits another car, okay, that's a collision detection. All sorts of things in game programming that boil down to that. Is this thing touching that thing? And that's done right here. All right, so before we move on, okay, we've looked at a lot of the programming. We've actually looked at all the little programming labs in this unit. It's so easy to just get lost in the curriculum and just do the activities and continue on without reflection. And I want us to pause and reflect because, good Lord, so many real computer science concepts were introduced in here. It's actually hard to believe. So let's see, what did we introduce? First thing we introduced, basic flow control. What does that mean? Sequencing. Execute this command, then execute that command, then that command, then that command. That's a sequence of commands, one after the other. That's how we program. That's one of our building blocks. The AP talks about it in the exam and actually calls it sequence. So at some point, it'll be important for the students to know the word sequence. For now, it's not. They're just using it. Right? It's just a concept that they don't even have, really, because they haven't identified it as a concept. It's just something they use in their programming already, even in Unit 1. So it's super cool. Okay? Ifs. Ifs let you choose between two different paths. So for example, if I already met this student, then say, hey, nice to see you again. If I haven't met this student, then say, hey, nice to meet you, right? So that kind of alternate paths, right? And in fact, the kind of technical term is alteration, okay? But everybody just calls that an if statement because that's what it is in most programming languages. So if statements let me choose between this or that based on some condition, okay? They've already seen that. They saw repeats. A repeat lets me say execute this sequence of code, this block of code 5 times, 4 times, 10 times, whatever, right? You choose the number. They saw that, okay? They saw forever loops. With a forever, it's like repeat this sequence of code from now until the end of time, right? Or at least until the user hits the stop button. They saw that, okay? They saw for loops, for I equals 1 to 10. Just like a repeat loop, but with the added bonus of having a variable, right? That tells you I'm in step 1, step 2, step 3, okay? That's another concept that we snuck in on the poor students. We didn't tell them that this thing is called a variable. We just kind of introduced the idea that this little thing can store a name, can store a number, right? Well, those are called variables, okay? That's what every language calls them. They're already kind of familiar with them, okay? They've already used them in their code. They've also used some basic data structures. I'm talking specifically about lists here, right? So a data structure lets you store like a collection of things, right? And the basic data structure is a list. I'm going to store these things, the first one, the second, the third, the fourth. They're ordered in some sort of a list. They've seen that, okay? They saw that in particular having to do with names, right? So here's a list that contains the names of the people I've already met. Beautiful, beautiful, okay? Something else I saw was procedures, okay? In other languages, they're called procedures. In Snap, they're called blocks. They're the exact same thing, okay? But they've gotten used to working with blocks to do something, okay? What else did they see? They saw abstraction, okay? What do I mean by that? They noticed, for example, that to build a polygon, you could actually use the pinwheel code. You just have to change this and that, right, to be able to do that. Oh, and an asterisk could also use the pinwheel code, right? So here's the trick question. How did your program benefit from this abstraction? Well, I was able to use it in two different contexts. I could use the pinwheel abstraction to build polygons. I could use the pinwheel abstraction to build asterisks. Beautiful, right? That's a great answer. That will get them lots of points in the create task for the AP exam, okay? So you see that we already actually taught them a lot of things. Now here is something that you will not actually find in like a Java 101 class, okay? Maybe not even at the end, okay? Throughout the entire semester. Concurrency, more than one thing happening at the same time. This is kind of I mean, it's so important in computing, but it's not something that we teach very often because it's usually so hard. But it's easy to do in Snap. We had two different sprites doing different things at the same time. So one sprite, say, might be moving randomly. The other sprite is following it, right? So you need two things to happen at the same time. You can't just kind of code one and then take a step and you do this, right? That makes it really hard to code. Instead, you let each one of them kind of decide what it wants to do by itself, and they both kind of work in the same area. That is concurrency. All kind of advanced programs today use that concept. And here it is in the very first unit, okay? Another thing that we saw that's pretty fancy is message passing. So one sprite actually talks to the other sprite and say, hey, I want you to do this for me, right? And by the way, what is it passing? It's passing commands. It's saying, I want you to execute these commands for me, right? And the other sprite will actually do that. That happens when you have those two sprites following each other. So that introduces not only this idea of message passing, but also kind of an idea that what I'm passing can be a bit of code, right? You don't have to just pass numbers or strings. You can actually pass code to somebody else. That is a super advanced concept. In fact, it's got its own name, higher ordered programming. Very fancy, right? Unit 1, done. Okay. All right. We did labs 1, 2, 3, and 5. We skipped over 4. There's a reason for that. Lab 4 is not a programming lab. It is a discussion lab, okay? We're going to get our students together. We're going to be social scientists. We're going to talk, right? We're going to try to find out the truth by the dialectic method, okay? So the whole point of this is to actually engage the students in conversation. I want them to learn about some of the consequences of having computers in the real world. I wanted to think about the consequences of having computers in the real world. And quite frankly, I wanted to articulate their thoughts, their biases, okay? Their prejudgments. It's okay. You don't have to kind of know everything ahead of time because you put something out there and there's somebody else who will say, yeah, but what about? And then we start having that discussion that we want to foster. That's what this is about. So this particular lab is about digital privacy. And what it does is it gives you some starting points, some ideas to discuss. For example, is privacy good, right? Who's threatening privacy, right? Why is this an issue? Is it ever okay to give up some privacy, or should we all be bottled up, right? Those are all kinds of questions that are worth discussing. I've done this with high school students, and I got to tell you, I am astonished at the information that I get back, because I have my own biases that tell me, well, high school students will feel strongly about this, like, for example, privacy, right? Because if nothing else, they don't want their parents to know about what they're doing. That's how I feel because of my own kids. But working with them, they're like, oh no, absolutely, yeah, let's get rid of privacy because we want security. What? Where did this come from, right? So you can actually learn a lot about what your students are thinking and the way that they view the world just by talking to them and doing this. So that's actually built into this.